All right, here we go. Unit 2, Lesson 4, Derivative Analysis Analytically. So we're going to take the key understandings we have from looking at the graphs of derivatives of functions, and we're going to put our blinders on. We're going to apply those understandings of the derivative just using algebra to draw the same conclusions, to draw conclusions about intervals of increasing and decreasing, about mins and maxes, and so on. This was a tough lesson, so this is actually going to be pretty heavy review for the first 10 minutes or so, and then I'll get into what's actually new for today. So just a review of some of our key points of derivative analysis, some of the things we established by looking at graphs. If your derivative is 0, the derivative is the slope of the tangent line, so your original function f of x has a horizontal tangent line. So the derivative tells you things about your original function. If the derivative of your function is greater than 0, if it's positive, it means the slopes of the lines that are tangent to that function are also positive. So that means your function's on the way up from left to right. It's increasing. Versus if your derivative is negative, your tangent line slopes point downwards from left to right. Your function is decreasing. And you can make those hand signals to tell you things about mins and maxes. If my derivative, if my tangent lines go from having positive slopes to negative slopes, I must have just hit a relative maximum. Positive slope to negative slope. If your derivative switches signs, you were at a min or a max. You just have to make the hand signals to figure out which one. Negative derivatives to positive derivatives would be a minimum. So that the derivatives tell you what is the rate of change of my function. You can tell whether it's on its way up or on its way down. And so just to really make that solid, let's look at that in a graphical form. So again, the derivative is the slope of the tangent line. I'm going to say that till my ears are bleeding. 1, 2, 3, 4. If we wanted to approximate the slope of the tangent line at 4, again, tangent line slopes, this is going to be more of an art here than a science. This is just to get the idea. You may come up with differently sloped tangent lines, but that looks like f prime of 4 to me. It looks like the tangent line at 4. It has a slope of up 1, 2, 3, 4, 5, it looks like, and over 2. So the derivative at 4 of this function equals 5 over 2, or at least approximately. Maybe it's 4 over 2 and my line's not great, but I get 5 over 2 there. All right, what is f prime of, when does f prime of x equal 0? So when do we have horizontal tangent lines? We have them at our mins and maxes. So we have 1 right here. The derivative is 0 at x equals negative 4. We have 1 down here at x equals positive 1. And we have 1 up here at x equals 5. So those are where we have derivatives equal to 0, horizontal tangent lines. And what I want you to see here is the connection between the horizontal tangent lines, intervals of increasing and decreasing, and mins and maxes. First, let's talk about when the derivative is less than 0. So if I talk about the derivative being less than 0, I'm talking about when this is a graph of f of x is going down. So all of my tangent line slopes, if I draw tangent line slopes all the way on these intervals here, that I'm going to shade in purple, my tangent line slopes are negative. My tangent line slopes are negative on these purple intervals, which happen to be from negative 4 to positive 1, from our first max to our first min, and then from our second max at 5 all the way to positive infinity. Those are where your derivative is less than 0 because your tangent lines, if you were to draw a line tangent to that function, sorry, I have to do this backwards for you, tangent to that function, they would point down. Versus our tangent lines are positively sloped the rest of the function. So in this green sections, which fills in from negative infinity all the way to the left to negative 4, and from 1 to 5. And as you can see, the places where we switch are where we have what we call local or relative mins and maxes. We have a relative max when the derivative goes from positive to negative, and we have a relative min when the derivative goes from negative to positive. That's going to be a really important idea for today. Like I said, we're just going to do one more piece of review because this is such an important topic. And I feel like it was a little rough when we did it the first time. What you could also be given is you could be given a graph of the derivative, meaning we took the slope of the tangent line at all of the points on some function, and we plotted those slopes as y values. So for example, if I look at what's happening here, this means that at some original function f of x, when x is -2, the slope of that function's tangent line was 0, because this is -2, 0. That's all that this means. It tells you the slope at a point. And so on what intervals is f of x increasing? This is not a graph of f of x. Well, f of x is increasing when the derivative is greater than 0, and that's just here. That's just from -3 to -2. That's all. -3 to -2, because f prime of x is greater than 0. That's all that's looking for. On what intervals is f of x decreasing? Well, f of x is decreasing when the derivative is less than 0. This is a graph of the derivative. This is not the original function. This already is the derivative. So as long as I'm below the x-axis, which happens from -2 all the way to +4, because the derivative is less than 0. That is a graph of the derivative. If the derivative is below 0, this is a graph of the derivative, then your original function is decreasing. At what values of x does the graph of f of x have a horizontal tangent line? A horizontal tangent line, we just showed above, is when the derivative of a function is 0. This is the derivative. This is the derivative, so this is going to happen at 2 locations. And so what I would say here is this would happen at x equals -2 and +2, because f prime of x equals 0. So it's literally just like you memorize these things. Oh, horizontal tangent line, derivative 0, that happens when we cross the x-axis at -2 and +2. That's all, -2 and +2. All right, now these are the tricky ones. At what values does the graph of f of x have a relative maximum? I'm going to go ahead and fill in the y here before, and then we'll look for it. So I'm going to say this is because the derivative of x switches, and this is a notation you can do, from positive to negative. If the derivative goes from positive to negative, you found a max. So where does that happen? That happens at -2. At -2, we already said there was a horizontal tangent, and we just learned the derivative went from positive to negative, because to the left, this is where the derivative is positive. From the right, this is where the derivative is negative. In the middle, we're at 0. And so this is going to be at x equals -2. At what values of x does the graph of f of x have a relative minimum? That would be if the derivative went from negative to positive. That never happens here. The derivative never crosses the x-axis from below. Now you might look at that 2 on the right, but what's happening there is the derivative, this is a graph of the derivative, is below the x-axis. So the derivative is negative. It's negative. It's getting less negative. It's getting less negative. At 2, the derivative is 0. Then it's negative again. So it's a saddle point. -, 0, negative. Negative's like a wave. -, 0, negative. It never actually hits a minimum value there. So I would say here, none, because f prime of x never switches from negative to positive. Even though it hits 0, it doesn't actually switch from negative to positive. Finally, last question, and then we'll get on with what's new for today. It's pretty quick. What is the equation of the line? As soon as I see that, I don't even read the rest of the question. Equation of a line. I need 2 things. I need a point, and I need a slope. And if I can get those 2 things, I'm good to go. What is the equation of the line tangent to f of x at x equals 0? First thing we need is a point. When x is 0, what's y? X comma y. Hey, they told us. We don't have to do any work here. They told us f of 0 is 3. 0 comma 3. there is your point of tangency. Second, we need a slope. The slope of the tangent line, most important sentence in calculus, is the derivative. We have a graph that tells us the derivative at any point. We have a graph that tells us here that the derivative, aka the slope of the tangent line at 0, is -2. That's what this tells you. This is like a lookup table for the derivative. When x is 0, the derivative, the slope of the tangent line to f of x is -2. And so we have a point, we have a slope, point-slope form, y minus y1 equals the slope times x minus x1. You could, if it's open response, you're done there. If you wanted to get fancy, you could say this is y minus 3 equals -2x. If you wanted to go all algebra 1, you could turn this into slope-intercept form, but completely unnecessary. If it's a free response question, that's where I'm stopping right there. We got that by using 0, 3 as a point, and the derivative at 0 is -2 as a slope. So key point here, when you have a graph of a derivative, it's like a lookup table. You can look up what the derivative is at any point, and you can use it to tell you things about the original function. All right, so here's what's new today. How do we do this? When we put our blaster shields on and we can't see the graph, I just give you what the function is, and I start asking you questions about it. When is this function increasing? When is it decreasing? And we're going to find that we can do this. We did this in Algebra 2, but it took us like 20 minutes, and you had to like find all the zeros and think about end behavior and multiplicity. Now that we know calculus, this is going to be so much easier because we can think about the derivative. We can think about the slopes of the tangent lines, and we can think about this in a much more clear way. We have our original function. Let's try to say some things about it. First thing we're going to do is we're going to apply the power rule to get the derivative. F prime of x is 3x squared minus 12x. That's it. That's the derivative using the power rule. Now, point 2, find the critical points. So we're going to base our analysis around our horizontal tangent lines. We're going to think about, okay, when do I hit my mins and maxes or our horizontal tangent lines? And let's think around there. So we want to know, when does f prime of x equal 0? When does f prime of x equal 0? Meaning, when does 3x squared minus 12x equal 0? This is going to employ heavy use of your Algebra 2 factoring skills. In this case, we can factor out a 3x. 3x times x minus 4. We want to know when that equals 0. So that's going to be x equals 4 and x equals 0. These are what we call our critical points or our critical values when our derivative of our function is equal to 0, because it's where important, interesting things are happening. Your function is changing. And so we're going to base the rest of our analysis off of this. We're going to create a sign chart to analyze this function. What I mean by that is we're going to draw a straight line, and we're going to say, okay, we know a few things. We know that when x is 0, we know the derivative is 0, because we just proved that above. We know that when x is 4, the derivative is 0. And we know that there's no other places where the derivative is 0. So whatever happens after these things is happening forever. This function is going down forever or up forever. And the trick is here, we just have to figure out not even really what the derivative is, just at these 3 intervals, 1, 2, and 3, is our derivative positive or negative? And you're going to get to a place where you're doing a lot of this kind of mental math in your head. And so I want to give you a first example of how we might do this. Let's say we want to know what happens on our rightmost interval. What happens after 4? We know at 4 the derivative is 0. What about after 4? Pick any number. Pick any number that's after 4. Why not 5? If we plugged in 5, f prime of 5, and eventually I'll stop writing this, I'll just talk through it. F prime of 5, well, f prime is 3x times x minus 4, would be 3 times 5 minus 4. That's going to be 15 times 1. That's going to be 15. as you're going to see in a moment, I don't even really care that it's 15. What I care about is that after 4, my derivative is positive. If I plug in any number bigger than 4 for those x's, those terms are both going to be positive. So it doesn't matter. After 4, we're positive. But when I do something between 0 and 4, then what happens is, let's say 2. If I find, and again, these are all unnecessary here, once you really get the idea in your head, f prime of 2, that's going to be 3 times 2 times 2 minus 4. Now your first term 6 is positive, but your next one is negative. You're going to get negative 12 for the derivative at 2. So we have a negative derivative between 0 and 4. Finally, if you go below 0, well, then both parts are negative. Say you do negative 1. You'd have 3 times negative 1 is negative 3. Negative 1 minus 4 is negative 5. Negative 3 times negative 5 is negative 15, is positive 15. So you have a positive derivative there. So make the motions with your hands. On the way to 0, our derivative is positive. At 0, our derivative is negative. Between 0 and negative 4, between 0 and 4, the derivative is negative. We just found our first maximum. It's negative. The derivative is negative all the way to 4, and then it becomes positive. So here are some things that we could say about this function. Some things that we could say. Number 1, f of x is increasing when the derivative is positive. And the derivative is positive on negative infinity to 0 and 4 to infinity. The reason for that is because f prime of x is greater than 0. Number 2, we could do the middle portion. F of x is decreasing on just that middle part, 0 to 4. Why? Because we just showed that the derivative is less than 0. Finally, we can say things about the mins and the maxes. We can say that f of x has a relative min, or let's do the maxes first, has a relative max at x equals 0 because f prime of x goes from positive to negative. The derivative is positive on the way to 0. It's 0 at x equals 0, and then the derivative is negative, so we have a relative max. Likewise, f of x has a relative min at x equals 4 because f prime of x goes from negative to positive. That's all. It's the same type of analysis. It's the same type of analysis that we would apply to a function graphically. We're just now applying this algebraically without getting that picture aid. So let's see one more, and that'll be good for today. Second example, just so you can see this all one more time. If we have 2x cubed plus 3x squared minus 12x, the derivative of this function is 6x squared plus 6x minus 12 using the power rule. I want to set this equal to 0, but before I do, I'm going to do some factoring. I'm going to factor out a 6 and make this x squared plus x minus 2. This is 6 times x plus 2 times x minus 2. And so our critical values, we're going to be equal to 0 at x equals negative 2 and, that should be minus 1 and positive 1. So we make our sign chart. To the left is negative 2. To the right is positive 1. And I just want to know what is the sign of my derivative on those available intervals. If x is bigger than 1, so if x is bigger than 1, if you plug in 2, x plus 2 will be positive, x minus 1 will be positive. We'll have 6 times some positive number times some positive number. This is going to be a positive interval. If we plug in, let's say 0, if we plug in 0, we're going to have 6 times 0 plus 2 is a positive number. 0 minus 1 is a negative number. This is going to be a negative between -2 and 1. You can't always assume that they're going to flip-flop here. That's going to happen a lot of the time, but not always. And finally, if we have, say we plug in -4, we're going to have 6 times -4 plus 2 is -2. -4 minus 1 is -5. All we really care about is that this is a positive number here, so there are intervals of increasing or decreasing. Here, we have f of x is increasing because the derivative is positive. Here, we have f of x is decreasing because the derivative is negative. And finally, here, we have f of x is increasing because the derivative is positive. We're going to have two last things to point out here. We're going to have a relative max at x equals 2, and we're going to have a relative min at x equals 1, because at x equals -2, the derivative goes from positive to negative. At x equals 1, the derivative goes from negative to positive. So that's it for today. What I want you to always be able to do to refer back to when you get stuck, refer back to. These are the key ideas. If you can keep, like, what's tough here is the algebra 2, not the calculus. This is the calculus. This plus the power rule. That everything else is algebra 2 and just kind of reasoning through it. That is the calculus there. Keep those top of mind as you do the stuff for today.